Good evening, students. Today we are going to see the concept of heap. So let's start with what is a heap. So heap is nothing but it is a complete binary tree or an almost complete binary tree. Now we have already seen what is the concept of complete binary tree, and in the further part we are going to look towards what is a almost complete binary tree. Here, in which the parent node can be either greater or less than a child node. Basically there are two different types of heap, that is a mean heap and max heap. So what is a max heap? Max heap is nothing but it is a tree in which the value of each node is greater than or equal to the value of its children node. As you can see the example over here, the value of a node is greater than or equal to its children node. So this is nothing but a max heap, and opposite to that we are having the mean heap, where we can say that it is a tree in which the value of each node is less than or equal to the value of its children node. So this is an example of a minimum heap. So here you can see that this is a parent and its value is less than its children. Again here we can see this is a parent and its value is equal to its child. So this is nothing but this is an example of mean heap. Next concept that we are going to see is that it has certain properties that are to be followed, that is called as a parental property. Now parent should or parent being greater or less is called as a parental property. Thus heap has two basic properties. One of them is it should be a complete binary tree and it should satisfy the parental property. There are some basic concepts that we have already seen, but again we are going to see it. That is nothing but level of a binary tree. Now what is the level of a binary tree? Means at what level the nodes should be. So basically the root is always at level 0 and any node is always at a level 1 more than its parent node. Next is that height of a tree. The maximum level of a tree is the height of the tree. Then height of a tree is also called as a depth of a particular tree. Next basic property or next basic concept that we are going to see is the complete binary tree. Now when we can see that a tree is complete binary tree is a tree in which all the leaves are at the same level or at the same depth. Also second thing is that total number of nodes at each level I is given or is computed by 2 raised to I. And third thing is that total number of nodes in a complete binary tree are given by the formula, that is 2 raised to h plus 1 minus 1. Here h is nothing but the height of a given tree. We can see example over here. One of the example given over here is that 2 raised to 0. Here we are having 1 node, 2 raised to 1, here we are having 2 nodes, then 2 raised to 2, which is the maximum height of this tree, and here we are having 4 nodes, and all together we are having 7 nodes that we have computed with the help of the formula 2 raised to h plus 1 minus 1. Now we are going to see what is almost complete binary tree. So almost complete binary tree has two basic concepts that we are supposed to look into. First is that each node has a left child whenever it has a right child. Here we can see the example of it. Each node has a left child whenever it has a right child. Again here also we can see each node has a left child whenever it has a right child. But this is not the case that whenever it has a right child it has to have the left child. That is means there is always a left child, but a left child there may not be a right child. Second important property of an almost complete binary tree is that the leaf in the tree must be present at a height h or h minus 1. That means all the leaves are on the two adjacent levels. So here we are going to see the difference when we can see a tree is a almost complete binary tree or not almost complete binary tree. As I have already told you, this is an almost complete binary tree. The reason is that whenever it has a right child, it has compulsory a left child. But you can see in this example, whenever it has a right child, it doesn't have a left child. So this is not a almost complete binary tree. Next is that properties that are to be followed by the heap. So we are going to see these properties one by one. First is that there should be either a complete binary tree or almost complete binary tree, that we have already discussed. This is a complete binary tree, so it can be a heap. Again this is almost complete binary tree, so this is also an heap, but this violates both the properties of complete binary tree as well as almost complete binary tree, so this can't be a heap. Next is that root of a heap is always contains the largest element in a tree. Here we can see the example of this. Here we are having 20, which is the largest element or largest node among all the nodes available in the tree. Again, same way, 10 is greater than 3 and 4, 8 is greater than 6. So we can say that this is a heap. And third important property of a heap is that each subtree in a heap is always a heap. Then only we can say that the complete tree is a heap. So we can see over here 10 is greater than 3, 4, 8 is greater than 8 and 7. So this is completely a heap. Next important thing is that we can implement a heap by using the array. So here how we are going to store the elements. Heap can be implemented as an array by recording its element from top down and left to right. Now this is the important part when you are dealing with a heap while storing it into the array. You have to follow these all rules when storing the heap into the array. See, firstly, the root node is stored at position a of 0. Here we are going to consider an array A. Next is that left child is at 2i plus 1 position in the array. Now I is nothing but it is a location, or we are going to consider the nodes one by one. As suppose this is 0, I, 1, 2, 3, 4, 5 and 6. In this way, this is the value of this I. Next is that right child is at location 2 of I plus 1 in the array A. Next is that the parent node is at I position in the array A. Here this is an example how this heap can be stored in the array. As we have seen, this root node is stored at a of 0. So this is our root node and it is stored at a of 0, that is 0th position. Next is that the left child is at 2 of I plus 1. This I is nothing but 0 for us. So 2 into 0 is going to be 0 plus 1, 1. So this 10 is going to be stored at first position. Next is that again I is 0 for us. So it is next element, that is 8, is going to be stored at second position, that is 8. Now next is the 3 value. Already this is 0, this is going to be 1. So the value of I here is going to be 1. So where this 3 will be stored with this formula, we can see 2i plus 1 means what? 2 into 1 plus 1 means what? 3 is going to be stored at third position in the array. So you can see over here 3 is stored at third position in the array. Next is that right child is going to be stored at 2i plus 2. Here the value of I is again 1, remember that. So we are having 2 plus 2, 4. So 4 will be stored at fourth position. Next is again we are supposed to store these children of 8. Now I value is going to be 0, 1, 2. So in this case it is going to be 2. So let's compute the value, or let's compute the address where 6 can be stored in the array. So 2 into 2, that is going to be 4 plus 1, 5. So 6 will be stored at 5th position. You can see over here, as well as the value 7, it is going to be stored at 2 into 2, 4 plus 2, that is 7. So 7 will be stored at 6. So it is going to be stored at 6th position in the array. So same can be seen with another one more example. You can see over here 8 is stored over here, 7, 4, this is as normal. Again left child, right child, so it is going to be stored here. Again left child, right child, it is going to be stored here. Now how and where this 1 can be stored? Now you are supposed to firstly compute the value of I. How it is going to be? 0, 1, 2, 3, 4, 5, 6. This value of its parent is nothing but 5. So you are supposed to go with the formula 2i plus 1. So I value over here is 5. So 2 into 5 is going to be 10 plus 1 is going to be 11. So this 1 will be stored at the 11th position in the array, as you can see over here. So in this way we can store the heap in the array. Next part is that ADT for heap. Now what is an instance for heap? It is nothing but heap is either a complete binary tree or a almost complete binary tree in which every parent is either greater or less than its child node. Then the second thing is that operations that we can perform on heap is firstly to create a tree, and next is parent dominance. This is one of the most important function when you are constructing a heap. What is it? It is nothing but arrange each node in a tree in such a way that each parent node in a is greater than its children node. This we are going to see with the help of an example. So this is all about the heap. Thank you.